We have our next speaker, Hinda Haned. And Hinda is co-director of the Cbki Lab and senior lead data analytics at Janssen Biologics. In 2018, she was named professor by special appointment at the University of Amsterdam, and her research focuses on developing solutions for best practices for safe and responsible data science. Modern-day decision-making systems based on machine learning algorithms have increasing impact on our lives. While these systems can be useful, they can also produce erroneous or biased outcomes, and there is often no possibility for meaningful recourse or feedback. In this talk, Hinda will discuss different definitions of bias and bias mitigation through so-called fairness algorithms. Drawing from practical examples, she will argue that the most fundamental question we are facing as researchers and practitioners is not how to fix bias with technical solutions, but whether we should be designing and deploying potentially harmful automated systems in the first place. Please welcome Hinda onto the stage. And yes, please ask your questions in the Q&A function. Hinda, please take it away.
Yeah. All right. Okay, let me share my screen. Okay. I'm gonna try it like this. And I don't know if this will work.
Yep.
Can you see my slides?
Indeed, we can.
Okay, fantastic. Great. Well, thanks, Jan, so much for the introduction. Indeed, so what I would like to talk about today is kind of my perception as a data scientist, as a practitioner in data scientist, about algorithmic bias and mitigation. As Jan said, indeed have this kind of two hats. I work for a company, but I'm also doing research at the University of Amsterdam. And I'm mainly interested in best practices for safe and responsible applications of data science. I want to tell you a little bit, very briefly, about the Cbki Lab that we've launched a few months ago. And if you're interested in development of responsible AI technology, I would invite you to take a look at our website and then look up some of the projects that we have and reach out if you would like to join some of the meetings and the meetups and the events that we have. All right, so why do we kind of want to talk about algorithmic fairness today, or in general about bias and discrimination? From let's say a kind of a simplistic point of view, you could say, well, there's a lot happening in right now when it comes to AI technology, and very often we see this in the media that some things have been that some things are going wrong, and that these stories are revealed either by scholars or NGOs or journalists. They all have one thing in common. It's about a task that was automated and then a system that's harming people more than it's actually helping them. And you've all heard stories in the Netherlands about welfare allocation software that tend to have more errors when it came to folks with a minority background. There is a lot going on right now in the AI community discussions about facial recognition and how it actually tends to fail on darker skins. A lot going on in terms of recruitment, automation, and how that can potentially be biased against certain groups, etc. So all of this happening means that the AI community is active, trying to find solutions to this, that legislators, ethicists, people actually think about AI and technology are trying to also find solutions to these problems. But what I would like to focus on in my talk is kind of the perspective of the data scientist, right? As in, you work for a company, you're a data scientist, your job is basically to deliver data science products. So how do you go about thinking about bias and potentially discrimination, and how do you deal with it in your day-to-day work? So let's start by some definitions. So when I talk about bias in my presentation, I mean the systematic errors that can create unfair outcomes. And this can be due to a number of factors: algorithmic design, so the way we make decisions about how we are going to represent a problem in our model, biased data collection. So sometimes we can have underrepresentation of certain groups, which means that we have biased data, and also in the way we select these target populations. And basically, if you want to automate a task or you want to rely on an automated system to make a decision, and if you have bias in your data, then you're going to perpetuate that bias and you're going to scale it, because typically algorithms are cheap, or they're becoming more and more cheap to deploy, and they will affect way more people than if you just rely on manual work. So we can't talk about bias without talking about fairness. So basically, fairness is trying to solve this issue of bias, and in particularly in our domain in data science, fairness tends to be defined as how outcomes of a particular model are assigned to a particular group of individuals. So it could be women, it could be underrepresented groups in general, but it always is this concept of if you are going to make decisions based on a model, what are the outcomes, how are they distributed across groups, for example. And the core principle around ensuring fairness in AI is that you want to avoid bias, so these systematic errors I was talking about, even if it is supported by the data, right? As to avoid perpetuating the existing discrimination. So this is what we call distributive justice. So typically fairness is a political construct. So someone decides at a certain point that we have to avoid bias and we have to intervene in order to ensure fairness. So we want to avoid harming individuals or communities. And the reason why I'm saying that the core principle behind fairness in machine learning, fairness in data science, however you want to call it, is that sometimes you might have people saying, you know what, if the data says it, if the AI algorithm picked it up, why should I care? So the whole point of kind of my position here is to say, actually, we do care, and you should care, because you are making a decision to make your model biased towards a certain group. So it's not independent of the way you have represented the problem that you're trying to solve, right? The data comes from someone. The data comes from people who have collected that data. So it's not, algorithms aren't just magical things that we collect, on trees. It's just things that people build. And if they're built by people, they have the potential of being biased. So again, connected to this concept of fairness, so if we say that our algorithms are fair, it means that they are not harming people, right? And it makes sense then to try to define what harm is. So I find it useful from the perspective of a data scientist who has to work on a product and deliver a product for a company, for example, to define these types of harms. And I also find it useful in terms of communication with the key stakeholders to try to explain some of the issues that people need to pay attention to when they're developing models. Typically there is harms of allocation, of representation, and what is called degraded quality of service. So harm of allocation is when you have a system that is going to allocate or withhold from certain groups an opportunity or a resource. And this is typically an economically oriented view. So you've heard a lot about examples of loans and discounts and recruitment. So typically if you're going to refuse to someone to go to an interview based on an automated system that screens their CV, you're withdrawing that opportunity for them. And if you've harmed them because, let's say, you made a mistake, that the system made a mistake, then that will be a harm of allocation. So harms of representation is typically when you have a system that is reinforcing the subordination of a certain group. So typically, if you do a search, on the search engine, and then you would have biased results where only, let's say, a subgroup is represented. So we all have in mind this example from a few years ago, where if you would Google CEO, you will only have images of male CEOs. So this is typically harm of representation. And degraded quality of service is when a system produces degraded user or customer experience based on their personal characteristics. So this could be making recommendations, for example, on an e-commerce platform that don't make sense, or that are actually harmful to you as a customer. It's not something that fits what you're looking for. And the reason why this is important is because typically when you are a data scientist, you won't be facing very, let's say, very clear examples of potential for harm of allocation representation. You'll be more toward dealing with degraded quality of service. And it's important to know about this and to read about it, because this is also how you're going to make the point of how you should be designing your systems to avoid this. So there are different types of bias that occur for different reasons. And I'll encourage you to read this paper that I'm referring here. This is actually a simplified version of all the great definitions that you can read in this paper, but basically dividing bias in three categories is also kind of a straightforward way of talking about it, especially in a data science context. So you have historical bias that reflects structural societal issues. I will give examples of each bias example. Representation bias, so certain groups are underrepresented in the training data, for example, and measurement bias is when your training data are proxies for some ideal features and labels, but they're not the actual data that you want to measure. So let me give you an example of historical bias. Earlier in my slide deck, you saw this article from the BBC, I think it was, about a recruitment tool from Amazon that was sexist. It was sexist in the sense that the women candidates were at a disadvantage compared to the male candidates. And when you think about the type of data that a tool like this will be training on, you'll see that it will be there will be an underrepresentation of women in the data, because by definition of, let's say, when you look at the data, women in tech aren't really overrepresented, and not even half of the population. So typically, if you go into train an algorithm on this type of data, you will end up having underrepresentation. And the reason why this happens is because historically women have been underrepresented in STEM, right? Underrepresented in these jobs. And so you know that when you're going to build a model that's going to do this type of automated decision making, it will be biased, because you just won't have the same representation of women in your data. Another example of bias is representation bias. So this is where you have underrepresentation of certain groups in your training data. This is a very nice example, and I encourage you to visit this website. They compared 3 facial recognition software, and they compared when the software failed. And interestingly, the software tend to fail when they had to deal with darker skins, but also darker skins from female subjects. And of course, after this was found out, some of the software developers were able to actually have more representative data and the trained data and fix this problem. But this is a very good example of when representation really matters in the data, and you have to pay attention to it. And measurement bias, this is a nice example of it. This was a summer of last year. As you may remember, in the UK, there was a story about students manifesting or protesting against the use of an algorithm to predict their grades, so that they can, at the end of the studies, of the high school studies, so that they can go to college or be accepted in the college that they wanted to go to. And this algorithm or this automated tool that was used was supposed to predict their grades instead of actually using the grades of the actual teachers. And the reason for that, using that, was to make it more fair, so that we would actually follow the distribution of, let's say, outcomes or of these marks from the students for the that they had to be comparable to the last years. So what the software ended up doing is actually discriminating folks that were coming from schools in less affluent neighborhoods, because instead of measuring the potential for success for each student, they were actually measuring the financial and economic circumstances of the schools themselves. So we weren't exactly measuring individual performance, but where the schools were located, and whether the students in those schools had a higher or a lower chance of receiving a good mark. And basically, this is measurement bias, because we're not really measuring the performance of the students, but just we're measuring something else, right? And this is typically, this is a good example, I think, for that type of bias. So now to the important question is, how do we actually mitigate algorithmic bias in practice? So it's a complicated question, and I only have 20 minutes to answer this, but I'm not really going to answer it. What I'm going to do is kind of draw your attention to what exists and what you would look into as a data scientist who's trying to solve a potential issue in terms of bias in your system. So many of you might know that indeed there is no unifying framework to tackle algorithmic bias. So there isn't kind of one way to do this, and it's not something that experts or academics or practitioners agree on. And in most cases, this is something that you're going to look at after a problem has been revealed. Rarely do we talk about systems that have been kind of fixed because we found out about errors before they were deployed. And of course, as data scientists, we know that sources of bias can occur throughout the data science pipeline. So it could be because of the population we're targeting, the data we've collected, how we build a model, and how this model is actually going to be used to make decisions. So we know this, and typically, I think a lot of data scientists try to do this. We look at imbalances in our data. If we do have sensitive attributes, such as gender or postcode, we would try to look at it and see if the outcomes of our model, how they are distributed across these different groups. But that's about what we can do. When you really look at it from a practical point of view, as a data scientist, you use the data that's available. Right? You're not going to say to whoever ordered your model, actually, I don't like this data, has potential for bias, and I'm going to try and collect different types of data for this project. This isn't really how it works in practice. And so typically what we would do then as a data scientist who's trying to solve this problem is look at what are the potential solutions. Since I can't really fix the data, I can't really collect new data. So what can I do if I have a suspicion that my model can generate biased outcomes, or if my data isn't kind of bias-free? So it's kind of natural to go towards these more technical solutions and towards these mitigation algorithms that I'm sure many of you have heard about. And these algorithms are meant to fix the data or constrain your algorithms so that you avoid a biased outcome. And typically, in this context, where you're trying to mitigate the bias that you have identified, you already have identified a sensitive attribute. You know what your fairness objective is, so you know the issue that you're trying to avoid, and you know what is your target in terms of, for example, having fair outcomes between groups, for example. You already know what type of interventions you want to make, so you already know if you want to fix your data that's biased, your model that's biased, for instance, or even the outcomes of your model, and then you're able to monitor your fairness intervention. So in my opinion, in order to use these algorithmic, let's say, mitigating or fairness algorithms, you have to have these four you have to make sure that you have all of these combined. So, of course, this is difficult in practice, because if you think about defining fairness by itself, you have a lot of definitions out there. So it's very difficult to decide which fairness metric you're going to trying to aim for in your model. And I'm not going to go through all of these, but I invite you to look at the paper I'm referring to. And when it comes to mitigation algorithms, there are three types that you can look at. So the ones that indeed are going to modify your trained data, the ones that are going to modify your actual algorithm and the objective function to incorporate your fairness constraint, or you're going to actually train your model and afterwards do something with your outcomes and intervene on the outcomes to enforce fairness. So you can look at the different algorithms that exist. This is not an exhaustive list, but I put them here anyway. And of course, as you can imagine, these are there are a lot of limitations to doing this in practice because your sensitive attributes have to be known, and sometimes even
your time is over. So let's wrap up, and I think we can go to the panel discussion. Yeah, thank you very much.
Okay. Do I have time to finish?
Sure.
Okay, great, thanks. Okay, so in this case, basically what I'm saying here is that in order to use these algorithmic, these fairness algorithms, you have to know what you need to fix. And in practice, this is almost impossible to know. All right. So I don't have much more time left, but I just want to look at this very quickly. And what it shows is that even if you would decide to use an algorithm to constrain fairness in your model, there are still a lot of decisions for you to make. And this is simply a plot that shows different algorithms. On the horizontal axis, you see the different sensitive attributes that were corrected for either race or gender. And on the horizontal axis here, you see the group parity. So you kind of want to have equality of treatment of different groups. And you have the accuracy here on the vertical axis. And basically what this shows is that there is a lot of variability in accuracy, but also in the fairness metric that these algorithms are supposed to ensure for you. So it's not clear what parameters to use. It is not clear how to prepare your data for these algorithms to actually be efficient. And okay, so I don't have much time, unfortunately, but basically my message is algorithmic mitigation is very difficult in practice, and often as data scientists, practitioner data scientists, we won't have the luxury to actually do that in practice. We really rely on this whole system we're part of, where we don't decide what data we use, and we are constrained by regulation. We're also constrained by the business needs. So I would just encourage all of you to read more about this topic and to find ways to keep the conversation open about trying to deal with bias in your day-to-day work. And I will finish with this. Thanks.
Hinda, thank you very much